So now before I go further, I'm just going to give some background on deep learning so we're all on the same page. And then I'll talk about automated machine learning, techniques for optimization, and then I'll get into the specific algorithms for NAS. Okay, so deep learning. So it's been studied since the 1940s. The original goal was to simulate the human brain. And since then, it's the goal nowadays is to do well in machine learning tasks. And it was studied consistently in the 90s and early 2000s, but it didn't really, it really wasn't a leading technique until around 2012, when most people consider the AI, the deep learning revolution. And that's when this new deep learning model called AlexNet was entered into an ImageNet competition. This is the same data set I mentioned on the previous slide. And this algorithm just beat out all the other algorithms by a huge margin, like over like 10% improvement in accuracy versus non-deep learning models. So that's when everyone was like, okay, so deep learning might be a really good technique. Okay, so that we're all on the same page, let me just go over the setup and how deep learning works, just a high overview. Okay, so in machine learning, we have training data. So say we have a bunch of images of flowers and elephants. And then we take these images and we give it to our model, and our model trains using this data. And then once our model is trained, we give it new data that hasn't seen before. So we give it a new picture of a flower, and we tell our model to make a prediction, and hopefully it predicts that it's a flower. Okay, so now how does our neural network actually do the training? So if you see the neural network in the bottom of this image, there are a bunch of these neurons, which are these little circles. And the inputs to the neurons in the first layer are just the pixels of the image. And each neuron is some linear function of all of its inputs. And we say a neuron is activated if a weighted sum of all its inputs is greater than a certain value. So then if a neuron is activated, it passes its value onto the next neurons. Okay, so in the next layers, the neurons take as input the neurons from the previous layer, and then they're activated based on a weighted sum of their inputs. And so on all the way until the very end, when the last neuron predicts flower or elephant based on some weighted sum of its inputs. Okay, so at the very start, we just randomly initialize all these parameters to random numbers. So the parameters are just the weights of the weighted sum of each neuron. So at the start, they're all just random numbers. So our algorithm is really bad at picking flower or elephant. But then we start to feed it in all the training data. And if it makes a mistake, we say you made a mistake. So then it updates all of its parameters to do a little bit better. And then after we do this for a really long time, we feed it a bunch of training data over and over. Eventually, the algorithm will get really good at picking between flowers and elephants, even on images it's never seen before. Okay. So this is just a really high overview of deep learning. Okay. So now I'll talk about automated machine learning. So there's a lot of complexity when you think about machine learning from start to finish. So when you get your data set, you might need to do data cleaning, data augmentation. Maybe you need to do feature selection or feature engineering. Then, of course, you have to pick your model. So maybe you pick a deep learning model. Maybe you pick something else like a decision tree or XGBoost. So there's a lot of components when you think about the end-to-end process. And AutoML is the area that hopes to automate all of this. So we're not quite there yet, but maybe in like 5 or 10 years, this entire process will just be automated for us. So we can just sit back and watch an algorithm clean our data, augment our data, etc. Okay, and then a subset of AutoML is hyperparameter optimization. Okay, so on the previous slide, I simplified it quite a bit, but there's actually a lot of these hyperparameters that affect how well our algorithm does. For instance, there's something called learning rate, which is a value we set, and it's basically how aggressively does our algorithm update its weights when it when it has a mistake. So if we set the learning rate too small, it'll take forever to learn. But if we set it too high, our algorithm won't get that great accuracy. So there's all these little knobs and dials that we can tune that'll affect the performance of our algorithm. And finally, there's neural architecture search. And this is, you can think of this as further a subset of hyperparameter optimization. Because when you really think about it, NAS is just a bunch of parameters, like how long is our network, how many nodes in each layer, what are the operations for each of these neurons. So really it's just a bunch of parameters and we're trying to find the best parameters. Okay, so that's AutoML. So now I'm just gonna talk about some of the optimization methods for all these different problems like hyperparameter optimization and NAS. And I'll talk about which ones are appropriate for which settings. So one way to classify different optimization methods is whether we have access to the derivative or if we don't have access to the derivative or if we know two derivatives. So a really common analogy is say that we're in a field and there's a big mountain on the field, but we're blindfolded. And someone says, we need to reach the top of the mountain on the field. So what do? Do we just walk around randomly? Well, hopefully what we'll realize is that we can feel the slope of the ground while we're walking, okay? And then hopefully we can try to walk up the steepest part so that we get to the top of the mountain the fastest. So this is an example where we know the derivative because we can feel the slope of the ground on our feet, okay? So the idea of walking up the steepest part, this is essentially what gradient descent is. It's an optimization method where we know the derivative of the function. And actually, so in my analogy, we're reaching the top of the mountain, but usually you want to minimize some functions. So we call it gradient descent, where we try to find actually the minimum of the function. Okay, and gradient descent is what we use to train neural networks. That's how we update all the parameters, if you remember from a few slides ago. But then how do we optimize all these hyperparameters? So this is like learning rate and other things like this. So usually for hyperparameters, we do not have access to the derivative. So then we have to do a different type of optimization called zeroth order optimization. And this is harder because we have less information about the function. But I'll get into methods for zeroth order optimization on the next slide. And then for completeness, there's also second order optimization or higher, and that's when we have access to two derivatives or more. But it's not quite as prevalent in deep learning since we can do something like Newton's method, but it takes a lot of computation. Okay, so now how do we do zeroth order optimization? Okay, so two really simple approaches could be grid search or random search. So if you look at the image on the bottom, so say we have two parameters we're trying to optimize. Well, one simple algorithm is to just pick 3 values for each of the parameters and try all combinations of those 3 values. So that's the image on the bottom left. It's called grid search. And then a slightly different method is we still want to try 9 possible configurations, but instead of picking 3 each and then trying all combinations, we can just pick randomly from the 2 parameters each time. So this is a slightly different algorithm called random search. And people have actually observed random search to do better than grid search. There are ideas because say there's one parameter that's really important and one that's not quite as important. It turns out random search, then we get to try 9 values of the important parameter, Whereas in grid search, we only try 3 values of the important parameter. Okay, but what if we want to do something smarter than just randomly searching? So there are a bunch of methods where we can adaptively select. So that means we try a few points, and then we use our knowledge on the value of those points to guide our search for even better points. So one leading method to do this is called Bayesian optimization. And this is something I'll be talking about quite a bit in the rest of the talk. Okay, so now back to the outline. So now that I've gone through background on deep learning, AutoML, and optimization, now I can formally define the problem of NAS. And then I'll go through all the techniques that people use to solve NAS. Okay, so there are 3 main components that make up a good NAS algorithm. There's the search space, so you need to define the set of architectures you're searching over. And then there's a search strategy. This is the algorithm you use to pick the best algorithm. And there's also something called evaluation method. So usually these searches are iterative, where we try one architecture, then we try another one, then we try another one. An evaluation method is how we evaluate the architectures that we try. Okay, so let me talk about search space first. So first we have to decide whether we do macro search or micro search. So macro search is where we have no idea what our architecture should be. So we just try a huge variety of architectures. We might even try like convolution networks or recurrent networks, because we don't even know if our data is temporal or would benefit from convolutions or anything. So usually people do macro search when there's a brand new data set, and micro search when they might have some idea about their data set, what might work, but they're really trying to get the best possible accuracy on their data set. Another strategy is called progressive search. And this is when we start by searching over a really small neural network. And then once we figure out the best small network, we add on more layers and search over those layers. So it's sort of like our network is getting bigger and bigger as we go. And then finally, one really popular technique is called cell-based search spaces. So this is when we want to have a really big architecture, we want to have a really expressive architecture, but we don't want to search over all of it. So what we do is we search over some small neural network called a cell, and then we just duplicate the cell a bunch of times. This is what you can see on the image on the right. So this is a really cool technique because the search space is smaller, which means it's easier to search over, but we still get a really powerful neural network in the end because it's duplicated so many times that our network is really powerful. Okay, so these are the different types of search spaces. Okay, so now I'll get into the actual algorithms. This is like really what defines different neural architecture search algorithms. So the first one I'll talk about is Bayesian optimization. And this is a really popular method. It's used by Google Vizier, which was Google's in-house hyperparameter optimization algorithm. It's used by AutoKeras, which is a popular open source NAS framework. And there are also a bunch of research papers about it, like NASBot by Kandasamy et al. And the reason it's so popular, it's a great method to optimize an expensive function. And that's exactly what deep learning is. It's really expensive to see how well a deep learning algorithm does. So here's the framework. So first we fix some data set, like say we're using CFAR, and then we define a search space. So just like in the previous slide. And then to be really concrete, we're trying to optimize over some objective function. And the function is the input is an architecture, and the output is the accuracy of that architecture after we train it. Okay? And the final component that Bayesian optimization needs is a distance function between the architectures. So this means, say we have 2 architectures, and they're only different by a single neuron, and it's just like the operation changes on a single neuron, then these two architectures are pretty similar. So their distance is small. So we would also expect their accuracies to be pretty similar. But if we have two completely different architectures, then their distance will be really large, and maybe their accuracies will be really different. So it's up to us to come up with a distance function when we define a Bayesian optimization algorithm. But usually you do something like this, where you compare the different cells or compare the different neurons in a neural network and see how different they are. Okay, so now our goal is to find the best architecture with the best accuracy. And the general framework is at the start, we just pick random architectures. And then we do this iterative process where we look at the architectures we already tried, and then choose a new architecture and evaluate it. Okay, so the heart of this method is how do we use the previous architectures to choose a new architecture? Okay, so how do we do that? So the way Bayesian optimization works is the most common method is to assume that our distribution f of a looks like a Gaussian process. And this is an assumption where we assume that our function is fairly smooth. Okay, so if our function was like really jagged, like on the left, then it would be really hard to search over it, because we try one architecture, it gets some value, and then we try an architecture right next to it, and its accuracy is completely different. So we assume our function is at least a little bit smooth, like on the right. Okay, and a Gaussian process, it's sort of like the function equivalent of a Gaussian random variable, where it's a function where the deviations look like Gaussian noise. Okay, and remember I said the Bayesian optimization is an iterative process. So in each round, we get more information about the function. So if we look on the right, we've already evaluated our function at 5 places. And so now we've narrowed down what our function looks like. So we're pretty confident that our function lies within the gray area. Okay, so as you can see, as we evaluate our function at more and more places, we get a better idea about what the algorithm is. Okay, so what does this look like for actual neural architecture search? Okay, so here the inputs are neural nets. So if you look at the top panel, we have some graph of the neural networks, and then we use the previous evaluations to guide our search. So for example, we probably don't want to try an architecture on the left, because we know it'll probably not do quite as well, because the architectures on the left weren't that great. But it's really tempting to try an architecture right in the middle here, because there's a potential that the architecture is really good. Okay, because the error bars, the dotted lines, are higher in the middle here. So this is what Bayesian optimization does. Formally, it computes the next architecture to try, which has the largest expected improvement. And the way it does this is by defining the Gaussian process and then computing the architecture that's at the tip of the highest potential point that our function could reach. Okay, so this is Bayesian optimization. Okay, now I'm going to get into a couple other different methods for neural architecture search. So next up, we have DARTS, which stand for Differentiable Architecture Search. This is a research paper that came out last year by Liu et al. And this is a really cool method because, as I explained a while ago, people usually take NAS to be a 0th order optimization problem, but they actually found a way to cast it as a 1st order optimization problem. So the reason people usually say NAS is 0th order is because because the different values we can try for the parameters are not continuous. Like say I'm deciding between an architecture with 10 layers versus 11 layers. It's not like I can try 10.5 layers. That doesn't make sense. But they actually use a cool technique to make all the parameters continuous. So if you look at panel A, before we start, we just have a bunch of unknowns for what our operations should be. For instance, like if you look at the rightmost edge, this operation could be a ReLU, a convolution, or a pooling layer. So their idea is why not just try every single one of those? So every place where we want to add an operation, let's just add every single operation we want to try. Okay, so then if you look at panel B, so maybe the red line is a ReLU, the green line is a convolution, and the blue line is a pooling. Okay, and we give parameters to each of these layers. So we give a parameter alpha, and the parameter represents how much we weight each operation. So the rightmost edge, maybe it's like 0.5 times ReLU, 0.3 times convolution, and 0.2 times pooling. Okay, so now we've successfully added parameters that are continuous, which means that we can do gradient descent on these weight parameters. Okay, so then it's a really interesting method because now that we've set up the parameters for the architecture, we can actually perform gradient descent, and we can learn the best architecture as we're learning the weights for the architecture. Okay, so it's pretty cool that we can learn both the parameters and the hyperparameters in parallel, both using gradient descent. So this is like a really cool method. So the upsides compared to Bayesian optimization is instead of having to iteratively try like a bunch of different neural networks, we only have to train one neural network. Okay, so it's just one neural network that's over parameterized at the start. But the downside is that this might only work in the micro search setting. So this might not be a good technique if we have no idea what architecture to use and we want to try a bunch of different architectures. But it seems like it's best suited when our search space is fairly small. And excuse me. And the reason is because we had operations on every single edge. Excuse me. Okay, so now I'm going to talk about one more method for neural architecture search. And this is actually the first method that, or not the very first, but the first that got really, really popular back in 2016. It's by Zof and Lee from Google Brain. And their idea is, well, we want to search for the best neural architecture. Let's use a neural network to search for the best neural network. So this is like a crazy idea, but they got it to work with really good results. So what they did is they defined a controller neural network, which is a recurrent neural network. And the framework is that in every round, it chooses a new architecture to try. And then once the RNN picks an architecture to try, we train that architecture and we see how well it does. We evaluate its accuracy. And then we pass that accuracy back to the controller. So then the controller gets some update like, oh, that one did well, or oh, that one didn't do so well. So then the controller uses that feedback to improve and get better at proposing new architectures that do well. Okay, so the way they set this up is a reinforcement learning problem, because the controller takes some action in each round where the action is choosing a neural network, and then it receives feedback. So like that architecture did well, that architecture didn't do well. Okay, so they set this up as a reinforcement learning problem, and they showed that this can be used for NAS. Okay, so the upside of this method is it's much more powerful than Bayesian optimization or gradient descent, because instead of like treating this as a Gaussian process or gradient descent, they use an entire neural network, so that it's much more powerful potentially than just treating it as a Gaussian process. Like neural networks are much more expressive, so potentially it can learn really complicated information flows to pick the best architecture. The downside is that this adds a whole lot of complexity. Okay, so not only do we need to learn a neural network, but we need to use a neural network to learn the neural network by training neural networks. So it sort of multiplies our complexity, which could make it pretty difficult to actually train this and get it to work. And the other downside is that some people have pointed out reinforcement learning could be a little bit of overkill, because essentially neural architecture search is just an optimization problem. We just want to optimize some parameters, but they're treating it as reinforcement learning, where you have the idea of a state and an action you can take and reward and transitions. So people say like the reinforcement learning framework might be overkill if we're just doing an optimization problem. Okay, but it seems that Google in particular keeps cranking out papers using reinforcement learning. So there's definitely some strength to this method. Okay, so those are the three neural architecture search methods that I want to talk about: Bayesian optimization, differentiable architecture search, and reinforcement learning. Okay, so now let me just touch on the final component of neural architecture search, which is the evaluation strategy. So remember, most of these methods are iterative, where we try one architecture, then we try another architecture, and so on. So the simplest thing is to just train each architecture we try all the way until it converges. So that's the simplest thing, and it gives the most accurate results. But the problem is that this might take a really long time. Like, it's common that architectures take hours or longer, maybe even days, to fully train. So then our algorithm will take a really, really long time. So people have proposed to maybe cut down the time by just partially training architectures. So maybe we train it halfway or like 1/10 of the way. So this will definitely cut down on the computation time, but it tends to be less accurate, because every once in a while, some architecture that does bad at the start might eventually do really well if we trained it fully, but we will never notice if we stop it early. And finally, people have also proposed methods called shared weights. And this is where, before we start our neural architecture search, we train some weights that work well for every single architecture in our search space. And then when we run NAS, we don't need to train our architectures at all, but we just evaluate them on these shared weights. Okay, so this is the least computation because we're not doing any training at all, but it also tends to be the least accurate. So shared weights might be an okay indicator of how well an architecture does, but it's not as good as if you actually train the architecture. Okay, so these are the three components of neural architecture search: search space, search strategy, and evaluation strategy. Okay, so now I want to touch on, so I told you all about neural architecture search, and let me just take a step back and tell you about how this field has progressed and where we are right now. So it really started in 2016 with the paper on reinforcement learning. And then there was a flurry of results in 2018 when these algorithms actually got efficient to compute. So at the very start, it was like you needed 100 GPUs and like months of training to get them to work. But in 2018, people started coming up with really efficient methods of doing this. So then there were a ton of research papers when everyone was able to start working on NAS. And this resulted in a bunch of different papers that are really hard to compare, because it turns out everyone uses some slightly different search space. So it's like comparing apples to oranges, where you can't really compare the search technique if they're searching over a different space. There's also annoying trend where the search spaces tend to get smaller and smaller. And the reason is it's every research group wants to get state-of-the-art accuracy because that sounds great, and then they'll get accepted to conferences. But to get state-of-the-art accuracy, it's easier if you have a smaller search space, because if you use your domain knowledge to come up with a really good set of architectures that's fairly small, then no matter what search strategy you use, you'll still get a pretty good result. So actually, just this past year, there have been a couple papers that show some of these search spaces are getting so small that even just doing random search, so just randomly picking one architecture from the search space, is already going to give a pretty good result. So there's sort of this about face in this NAS literature now, where a bunch of different methods have been proposed, and then people are like, oh, but random search is also doing well. So we're just starting to see some papers coming out that give fair comparisons between these algorithms. But I would say we're not quite at the point where we can say, like, this is the best method, this is the best algorithm. We still need a bit more work in showing fair comparisons between all these different methods. Okay, so I can't really say, like, what is the best neural architecture search algorithm. And the other thing is NAS is showing a lot of promise. I would say, especially on brand new data sets where we have no intuition, NAS is really well suited for these areas. But we're not quite at the point where NAS can consistently beat humans on all data sets. For instance, unlike CFAR10 or ImageNet, still humans are much better at coming up with architectures than neural architecture search. So there's still a little bit more work to be done, I would say. I think NAS is a very vital area of research for AutoML moving forward. But right now, it's not quite ready for widespread adoption. So if you want to get into neural architecture search, I recommend so AutoKeras is totally open source, and it's hyperparameter optimization and neural architecture search. You can find some tutorials online, like this link here. And then most of the papers I talked about, like DARTs and papers on NAS for Bayesian optimization and reinforcement learning, they're all open source. So I give one example here, the DARTs paper, all the code is online. So you can download it like today if you want. Okay, so I'm just to wrap up. So I talked about NAS, which is finding the best neural architecture for a given data set. There are three components, which is search space, search strategy, and evaluation method. I talked about three search strategies: reinforcement learning, Bayesian optimization, and continuous optimization. And I talked a little bit about how close we are for widespread adoption and the state of neural architecture search research. Okay, so now I can take questions.
Great, thanks for the talk. If you have any questions, you can either type in the chat window or in the Q&A sessions. I think there are a few in the Q&A sessions. Can you take a look at it?
Sure. So let me look. I'm scrolling through all the questions. Oh yeah, I can add the slides. Maybe I can send you the slides so that
yes,
people can download.
Yes, you can send me the slides. I'm going to send the link in the post email.
Okay, let me see. I'm still, yeah, so I didn't go through any code today, but I gave links for, there's a bunch of code online. Okay, so, so I see one question. Is DARTs only used for the operations between layers? For Bayesian optim. Okay, yeah. So yeah, DARTs actually does search for both the operations and the connections between layers. So I didn't really go into all the details, but one way you can search for the operations and the actual connections is if you you just start with a complete graph, like a completely connected graph, and then you add parameters to every edge in this graph and every operation, and then you start to do the search on this, and you'll find the most important connections have the greatest weights near the end. And you can also start to do things like dropout, which is a common technique for regularization, where you prune down some of the edges so that you don't end with like a completely connected graph. Yeah, and so Bayesian optimization, it's more clear why you can search over like really complicated graph structures. Yeah, so I sort of, so yeah, darts can also search over these complicated graph structures. Okay, I see one other question. How well does the assumption the architecture space is Gaussian hold? So this depends on a lot of factors. So it's kind of funny, to do this hyperparameter search, we need to define hyperparameters. And this is like how, so Gaussian processes themselves have parameters like variance and stuff, like how much variance it is. So we can actually tune our assumption about how Gaussian the architecture space is. So if we think that our architecture space is like really complicated, we might assume that the variance is really high. And we can also assume that it's more smooth, but then we might be wrong, and then the assumption doesn't hold quite as much. So there's a trade-off. If we assume it's higher variance, then it's harder to search over. It also depends on the distance function. I said that it's up to us to define the distance function. There are a few different ways of doing this in practice, and some ways are better and make this assumption hold better than others. Okay, so is NAS for lazy data scientists, or are there specific use cases for this technique? So they always say the best programmer is a lazy programmer. So it used to be the case that grad students would try to find the best architectures for their professors, and they would just try all possible combinations. But then this field of NAS sort of automates that so that grad students don't have to just try all these things by hand. And I can see in the future NAS is used to get state-of-the-art on any data set. I would say right now the best use case is for brand new data sets where we have no intuition on what architecture to try. But yeah, nowadays it's better for brand new data sets. Yeah. Okay, so what hardware specs are we using at realityengines.ai? So realityengines.ai is a new startup. We're just a few months old, and our goal is automated machine learning, so an end-to-end platform for AutoML. I don't think I can talk. I don't think I can give away too much about the actual hardware and things we're using, but we're trying to keep up with the best companies in AutoML. Okay, so are these methods used in the current market? Okay, so I would say as of right now, NAS is more common in the research setting. So you'll see more like Google Brain and academic papers about NAS. It is, I think it's also being used in the current market. For instance, like AutoKeras and if you've heard of Google AutoML tables, this is like Google's attempt at automated machine learning. I assume that they probably use NAS because they have a bunch of papers and they get pretty good results in their AutoML. So so I would say it's mostly research. There is some use of NAS in the current market, but only like the top companies that have access to a lot of computation power are using NAS right now. For use cases, really use cases, anytime you want to use deep learning, NAS will probably help you if you have the computation power. Theoretically, NAS can improve the accuracy on any data set because ideally it'll just find the best architecture for your problem. Yeah, so I can give the slides. So what fields? So so I would say one of the greatest successes for deep learning has been computer vision. For instance, there are so many different convolutional architectures that are proposed. I listed a few at the start. There's like ResNet, InceptionNet, DenseNet. There's so many of these. So I'd say the techniques for computer vision are the most powerful applications of deep learning in general. And so we're also seeing this is true for neural architecture search because we have such a good idea about like what ingredients make up a good computer vision or CNN architecture that that we're really good at discovering good CNN architectures. And so then for NAS algorithms, we can have it search over all these ingredients and find even better architectures. So a bunch of the academic research focuses on data sets like CFAR10 or ImageNet that are these image data sets. Okay. Is the search space shrinking because the nets are always evaluated on the same data set? Yes, so that is exactly true. So there was this trend in the NAS research where everybody used two benchmark data sets. They used CFAR10 and Penn Tree Bank. So CFAR10 is an image data set, Penn Tree Bank is a text data set. And yeah, so so since everyone was kind of converging on these two data sets, it would be common that from paper to paper, the search spaces became better and better until the search spaces were fairly small. So so then as I said in the talk, then the search space is so small that no matter what search method you use, you can get really good results. Yeah, so is darts interesting on the theory side? So yeah, there's actually really nice theory in the darts paper. So I mentioned in the talk that you kind of learn the architecture and the parameters in parallel. So they actually have some cool theory to show that they can do this where you make one iteration of SGD for the parameters, then make one iteration for the hyperparameters, and you go back and forth. And they show that, as I recall, if you write this out as an optimization problem, it's NP hard to solve the exact solution, but they show that their iterative process of like updating one at a time still is a really good heuristic for converging to the optimal architecture and parameters at the same time. So yeah, I would recommend I linked to the GitHub of the darts paper. You can also find the darts paper online by searching darts differentiable architecture search, and all the math for that paper is in there. Okay. What technology stacks are you using and common in this field? I'm not sure if that means neural architecture search or if that means my own company. But I guess for both ways of that question, just any place where deep learning is applied, neural architecture search can be used to improve deep learning. Okay, about the shrinking search space. Yeah, so one person asked about the shrinking search space. Does it make sense to actually increase the search size so that we can arrive at one architecture? Oh, I see. So for the first half of the question, I definitely agree that that this shrinking search space phenomenon was just sort of like a technique researchers use to promote their papers because they say they get state-of-the-art accuracy. whereas even if their search algorithm wasn't quite as good. And then then you ask so that we can arrive at one architecture to find algorithms for any given problem. I think that's a really interesting question. It's sort of a tangent, but the question is, does there exist one architecture that can be used for multiple data sets? I haven't seen any evidence of this, but it's a really interesting question. Like maybe there exists some architecture, or maybe we can search over some architecture that does well on multiple data sets. So nowadays, usually you first fix your data set, then you pick the architecture. But it's an interesting question. Maybe there's one architecture that does well for everything. Why is AutoML not yet industry adopted, e.g. Google AutoML? So I mentioned Google actually does have an AutoML platform now, and there are a bunch of other companies like I think in the chat people mentioned like H2O.ai and RealityEngines.ai. So AutoML is starting to get adopted. There are definitely some like hyperparameter optimization is getting pretty good nowadays. NAS is still fairly on the research side, but definitely there already are platforms for AutoML that does like hyperparameter optimization, maybe some data cleaning and things like that, and model selection. Is it also good for time series like RNN and LSTM? Yeah, so most of my examples were for image data sets, but actually most of these research papers, they test two data sets. In fact, I already mentioned this replying to another question. So most of these algorithms did experiments on CFAR and Penn Tree Bank. So they did find the best LSTM, and yeah, they searched overall LSTM networks. So all of the strategies I talked about also work for recurrent neural networks. Okay, so how close are we to do NAS in real time? So NAS, so the first paper in 2016 took like an insane amount of compute time. Like Google threw all of its like 1,000 GPUs at the problem. So it was like thousands of GPU hours or GPU days. And then, but just in the past year, all these algorithms are getting much more efficient. So now it's just like a single GPU day or half a GPU day. So this question asks, like, can we do this in real time, like almost instantaneously? I think, yeah, it spits out an architecture. Yeah, so definitely we're getting closer and closer. We still need about half a GPU day to run these leading methods. So we're still a ways off from really quick NAS algorithms, but we're definitely moving in the right direction.
Okay, we have a couple of minutes left. Let's see if we have any questions.
What technology stacks are you using? So I think the majority of AutoML research and deep learning uses Python, because there are just so many packages like TensorFlow, PyTorch, Keras that are all in Python. So that's true of reality engines, and also any of the research I mentioned. If you look at the GitHub, I think it's all in Python. Yeah, so NAS has successfully been used to come up with LSTMs. This is like all the papers I mentioned, they usually have search over LSTMs. I mean, it depends on the search space. So like you can set up a really small search space for LSTMs, but I guess the question is, can NAS actually do like big macro searches? So there is definitely there are several papers that do macro search. So the actual numbers, the results they get aren't quite as good as these micro search papers. So I think there's still a little bit more work to be done before NAS can come up with like really strong algorithms for macro search. But definitely, I think in a couple of years, it'll be NAS will be really powerful even for macro search. So one person asks the ENAS paper. So let me think. ENAS, that's one paper, efficient neural architecture search. I think it's actually reinforcement learning. I think ENAS was using weight sharing for reinforcement learning. Yeah, so ENAS is not a Bayesian optimization. Okay. Should I do like one or two more questions?
Yeah, we are. Yeah, if I have one more question, maybe we can take one more.
Okay, so the final question, how big or what is the range of the neural architectures in the search space? Okay, so if you remember from my slide about search spaces, so I think the most common technique is to use these cell-based search spaces where we search over a small cell, and then to get a good neural network, we duplicate the cell a bunch of times. So a bunch of the papers I read, the cell is actually size like 7 or 8 neurons. So that means it's a fairly small neural network. So there's these 8 neurons. Each of them have an operation, maybe like 7 operations that each neuron can take. And then we also learn the edges between these neurons. So we learn the graph structure over these 8 neurons. Okay, so I would say it's fairly small. It's just eight neurons that we're doing the actual search over. Okay, great.
All right.
Thanks
Okay.
everyone for tuning in.
Great. Well, thanks a lot, Colin, for the great presentations, and thanks everyone joining us today. I hope you have something learning, and hope to see you next our event.
Thanks. Okay, I just